From the studios of Way Happy, this is Mr. Meyer in 2.6 graph of rational functions. So when you have a function divided by a function, that is what we call a rational function. So a bunch of x's on top, bunch of x's on the bottom. Now you probably remember, or you probably have heard, that there's these things called vertical asymptotes. That's what the graph cannot touch. So they're vertical, and they are when the denominator equals 0, right? Assuming they're not also in the numerator, because then they would cancel and that would cause a hole. Now, the end behavior asymptote, also known as the horizontal asymptote, also known as the ha when I'm feeling lazy, is a little pattern that you have to know. And that pattern is this. You compare the degree of the numerator and the denominator, and then you follow that little chart. If the numerator is less than the denominator, then the horizontal asymptote is y equals 0. If they are equal, then you take the leading coefficients, a over b. And if the numerator is more, then you have no horizontal asymptote. And it's all kind of based off of, a line, a y equals x line, and also a y equals 1 over x line. And just so you know, it has to do with just reducing and getting that asymptote. Now, this one that said there's no horizontal asymptote, just be careful because there is also a different type of asymptote there. This last one, it's when the quotient of the rational function. So the end behavior follows whatever the heck that you got if you would divide those two things out. And that's where long division really comes in helpful. And we'll do some of those. But let's move on. We got x-intercepts. You know what x-intercepts are. And y-intercepts when x is 0. And so let's use this information to try to graph a nice little problem here at the top of your screen. So what do I have? I have this beautiful thing. The first thing you're going to want to notice is that you're going to really like to factor this all down. And so I'm noticing I can pull out a 2 out of the top, and I'd be left with x squared minus 9. And oh my gosh, that factors to x plus 3, x minus 3. And so that's nice. Top's factored. What about the bottom? Can't pull a 2 out, darn it. So a little scratch work here. What two things multiply to 30 that add up to negative 11? Negative 6 and negative 5. Beautiful. Divide them both by 2. And it looks like one factor is x minus 3, and the other factor is 2x minus 5. So x minus 3 and 2x minus 5. And notice now I have factored everything, and I am feeling very good. All right. Now that I've done the factoring, I'm going to finally answer some of the questions. And the first question is, find the end behavior and the horizontal asymptote. Well, remember what we do. We compare these exponents. They are the same in this case, so we will look at the leading coefficients. So the ha, the horizontal asymptote, is when you look at those leading coefficients for this problem, and you get y equals 2 over 2, or what most of us would call y equals 1. And that is our horizontal asymptote, also known as the end behavior asymptote. So what I'm expecting is the limit as x goes to negative infinity, so the left side, I expect the function, I guess it's h, I expect h of x to go to 1. And the limit as x goes to infinity, the right behavior, I'm expecting the function also to head to 1. So again, I could use that little plus or minus, and I could say, boom, there she is, right? That is the end behavior. I would be expecting this graph to mellow out at 1. Find any vertical asymptotes, part B. So part B is beautiful because notice if you look at my factored form, it looks like x cannot equal 3, so a vertical asymptote I would think is x cannot equal 3, so x is 3 is a vertical asymptote, and x is, what is that, 5 over 2? So 5 over 2 or 2.5. But then notice something. The x minus 3 is actually a removable discontinuity. I can cancel those, and they're gone, right? So the new problem is actually 2 over x plus 3 over 2x minus 5. Now, the bad thing about removable is you have to remember it was there. You can't just remove it and pretend like it was never there. We removed it, this new function right here. This does not care if x is 3. But remember the original? It did care. So even though it's not a vertical asymptote anymore, it's now called a hole. So what will happen is it's not a vertical asymptote, it is just a hole. So a hole at x equals 3. But the other one is a vertical asymptote, and I'm feeling a little better. Now, what do? You would just graph this graph over here, and then make sure that you put just a little hole at 3 to let everyone know that the graph was there. And so maybe I'll try it. 2x squared minus 18, I can probably put in Desmos. So 2x squared minus 18, 2x squared minus 18, and darn it, I should have put that all in parentheses, right? Because I want it in the numerator, divided by, now what did we have in the denominator? We had 2x squared minus 11x plus 15. 2x squared minus 11x plus 15. 2x squared minus 11x plus 15. And you see that beautiful graph. And we had something cancel. And what did it cancel? We had it cancel at 3. So if you look way up here at 3, I don't know why it's drawing in that asymptote. If I kind of plot this, oh, I'm not high enough, darn it. Let me see. Look right here. Where's 3? There you are, 3. Boom, look, that C, undefined. So see that undefined right there, 3? There's actually a hole on Desmos, but we would have never found that if I didn't know it was there. And so that's something you want to watch for. All right, let me ask you a question, and we'll be right back. All right, beautiful work again. Now let's look at this next example. I want to graph this bad boy. So again, you're going to do kind of same thing. You're going to look for vertical asymptotes, horizontal asymptotes. You're going to try to find x-intercepts and y-intercepts, and then do your best to graph it. So let's give it all a big shot here now. So first thing I'm going to do is find the end behavior, the horizontal asymptote. So again, I would probably, usually when I see one of these, my first instinct is to factor. So multiplies to 8, that adds up to 6. That's what, x plus 4, x plus 2, all over x plus 1. Okay, nothing there, cancels, so that's good to know. Find the end behavior. Okay, we'll do that. Compare the exponents. Ooh, bigger on top. That means there's no horizontal asymptote. But what that does mean is there is some other type of asymptote. And the asymptote you want to find is one when you divide that out. So you actually do the long division. So I'm going to be like, all right, x plus 1 goes into x squared plus 6x plus 8. Now, hopefully this one's not too scary. So I'm going to multiply it by x and get x squared plus x, do the sign changes. Probably should have left myself some room. 5x plus 8. And then I do here, I get plus 5. And now I'm kind of done because 5x plus 8, sign changes. I'm sorry, 5x plus 5, sign change. Gives me a remainder of 3. But when you're finding the asymptote, the oblique asymptote, they like to call it, when you're finding that asymptote, you don't really care about the remainder. You just care about this guy. Now, if he's the first power, then he's a linear or a slant asymptote. If it's the second power, he's a parabolic asymptote. And so those would be things that you'd want to put in. If third power, it's a cubic asymptote. So this is what we call a slant asymptote. And his equation is y equals x plus 5 because that's what I got when I did the actual division. That was the quotient of the division that we have in this problem. Now that's going to be super important in a little bit when I come to graph. In fact, change that. Let's graph it now. So I see step E is graph this thing. So here's my graph paper. The very first thing I'm going to notice is that I have an asymptote or a slant asymptote with the equation x plus 5. So what does that mean? 1, 2, 3, 4, 5, boom. And then go up 1 over 1 and connect those. And that is what we call your slant asymptote. So there's your slant asymptote on your paper. Now, funny thing about horizontal and slant asymptotes, that's what the graphs want to be. It would love me to just fill in that line and be done, but I can't yet until I check for what we call vertical asymptotes. So let's check for vertical asymptotes. Vertical asymptotes, set the denominator equal to 0. Well, that's easy. X is -1. That's our vertical asymptote that the graph will never, ever, ever be allowed to touch. So it cannot touch this line. So now you can see that the graph would love to be on that slant asymptote. It wants to be on the red line. But then all of a sudden it can't because of the blue line that it can't touch. And so we got to see what happens. All right, x-intercepts are when the fraction that you're graphing equals 0. Well, the only way the fraction could equal 0 is if the top is 0, and that could happen 2 times. So it appears that we have an x-intercept at -2, and it looks again like we have one at 4, which I don't know, is probably about here. So we have some x-intercepts. Nice to know. Y-intercept would be when when we plug in zeros for the equation. Probably easier to do in the original. So I would get 0 plus 0 plus 8 over 0 plus 1. So it's 8. So let's see, that was 5, 6, 7, 8. Right here is my y-intercept. And now sometimes that's enough information for you to graph. And in fact, for me, it is. I'm feeling really good. I know the graph wants to be here, right? Wants to be on this line. Maybe I'll highlight it. The graph wants to go like this, right? That's what it wants to do. But it can't, because as it's cruising along on that line, what's going to happen is it's going to freak out at the infinite discontinuity, the blue line, and it's going to go either straight up or straight down. So according to my 2 x-intercepts here, it looks like the graph must be going like this, and then it's going to see that, and it's going to turn, and it's going to get out of here. So that's what it did. It traveled along and freaked out. Well, it's going to come back from its freak out because the x values, the domain, what happens at -0.5, right? Well, because of the y-intercept, it looks like it's way up here. Looks like it's going to come down, hit this guy, and then it's finally going to get back on that red line and be out of here forever and ever and ever and ever. And so that's what this graph would look like. It would look just like that. There's no holes or anything. It really wanted to be that slant asymptote. If it was a parabola asymptote, it really would have wanted to be that parabola. It just freaks out at infinite discontinuity, but then it comes back and continues on its merry way until it sees another one. And luckily it didn't see another one, but I bet you the next one will. All right, let me ask you a question, and we'll be back in a few. All right, excellent work. And now let's do this example where I give you nothing. I just say graph it, go. No graphing calculator, I should probably say. But just do a nice little graph and tell me how it all turns out. All right, you are Desmos now. And so there's all the things you have to worry about. There are things like what we've kind of led up to. We want to know the asymptotes. So first I'll do the horizontal asymptote, which says compare the exponents. Ooh, bigger on the bottom, so it's automatically y equals 0. So that's nice. We know that this is the end behavior asymptote. Again, this is where the graph would love to be. If there was nothing else going on, I would just draw that line in and I would be finished. I'm going to find what we call the vertical asymptotes. That's when you set the denominator equal to 0. Now, I probably wish I would have factored this first. So let's see, the top didn't do anything, but the bottom, what is that? X plus 3, X minus 1. Yeah, looks good. So nothing cancels. And so there's no holes. That's always nice to know. Bad news is right here, you have X equals -3 and you have X equals 1. Now, the reason that's bad is now the graph is going to freak out twice, not just once. So 1, 2, 3. Here is one freak out for the graph. And that's a technical term. And then here is another freak out of the graph. So kind of visualize what's going to happen here. The graph's going to be, I'll do it in the highlighter. Graph's going to be coming along and then it's going to freak out. It's either going to go up or down. We're going to have to figure that out. Then it's going to come back either from the top or the bottom. And it's going to try to get back on this line, but then it's going to freak out again, either up or down. I don't know which way. And then it's going to come from the top or the bottom again. And it's going to come down and finally get on that line and be done. Now, I don't know which one it's going to do. So don't take that all into like, ooh, you said it was going to go up, because I don't know. Now, maybe I can find some more hints. Like, remember, there's cool hints about x-intercepts. So x-intercepts, right? Where are the x-intercepts? Well, that's when this equation equals 0. When does this equation equal 0? When the numerator is 0. So whenever the heck 3x plus 1 equals 0, that's 3x equals -1. That's x equals -1/3. So when x is -1/3, there's an x-intercept. That's not very exciting. I was hoping for more. A y-intercept would be when you plug a 0 in. Again, that's easier to do in the original function. So that would be 1 over -3. So we have a y-intercept at -1/3. That's probably not the most helpful thing either. What a shame. And that's all I got. That's all I have to work with. So kind of a bummer, but not too bad, because I might even factor this 3 out of the top real quick, because I'm going to now do a sign chart just to make my life a little easier. I like to have all my terms be x plus something. I'll show you what I mean by a sign chart again. We're going to graph this bad boy, and luckily it's hugging the x-axis. So we know it's starting over here and it's going that way. But the question is, where's it going to go? Oh, what just happened? It's going to disappear. That's where it's going to go. No, it's going to go this way, right? Guess I can't scribble. Now, we know it's going to travel on there. It's going to freak out when it sees that vertical asymptote. So let's figure out where it freaks out. Well, let's plot -1, 2, -3. -4 is a little too far. I'm going to plot -3.1. So I'm going to test -3.1 because that's just to the left of this asymptote, and I'm going to see where it is. So you could use a calculator, that'd be great, but I'm not going to. I'm just going to plug -3.1 in, and what would happen? Well, the numerator would be negative, and the denominator would be negative and negative. So that's a negative over a positive, and that's definitely negative. So I can already tell you that the graph's going to go heading this way. So I will say it's going like this, and then it's going to freak out and come down, and it's going to look like that. So we got the first part done. Now we got to decide on the other side of the infinite discontinuity, where the heck is it coming from? Is it coming from up here, or is it coming from down here? Well, again, I will test a point. So I will test the point -2.9, very, very close to that asymptote. Plugging in -2.9, I have a negative over a positive and a negative. So that to me is positive, meaning the graph is now all of a sudden magically up here, right? And it's coming back down because it wants to get on the horizontal asymptote and live its life till forever, unless it sees another vertical, which we both know it's going to. So let's see, it's coming down, and then it's going to freak out right here at 1. Well, it looks like, according to my intercepts here, it looks like it's going to go down. So that's fine, but I'm not 100% sure. I'd really like to test 0.9. So I'm going to test 0.9 because that's right on the other side of this, on the one side of this asymptote. So what would I have? I would have a positive over a positive and a negative. Oop, it does go down. It is negative. So notice this graph must come down. It must finally get on it. And then it's like, oh my gosh, I'm out of here again. I'm scared to death. And so it finishes like that. And look, it did cross its horizontal. So many kids would be like, oh my gosh, you crossed the horizontal, but you're allowed to. It's just a horizontal asymptote. It just tells me where it's going at the end. It is the end behavior asymptote. So now I just need to figure out, where is it on this side? Is it up here or is it down here? And again, how would I test? I'm going to test this point right there. What is that? 1.1. So I am going to test the point 1.1. And if I test 1.1, I will get a positive over a positive and a positive. It's all positive, so I know it's up here. And I don't have to test anymore because I know it's going to come down, and then it's going to get on this asymptote, and it's just going to ride its way on forever, because that's the end behavior asymptote. It is done doing weird stuff. And that, my friends, is how you graph a very difficult graph, right? And if there was more vertical asymptotes, we would have more. If there was a parabolic asymptote, we would have traveled on the parabola until we saw those verticals, and we would have panicked, right? So nice work. Oh, and if there was a hole, now I would go back and fill in the hole. Like, just say that there was a x-2 factor here and an x-2 factor here, and we crossed it out. We would have crossed it out. We would have done everything we just did, but then we would have gone to 2 and said, oh, there's a hole right here. And that's how people would have known that there was a hole, or at least that's how the graph, what we would know about the graph. That didn't happen, but I just wanted to mention. All right, have a great day. I'll see you tomorrow. Stay happy.